So what we're going to look at in this video is what happens when our ionic solids dissolve. Why do ionic solids dissolve? So ionic bonds, we've just said, are so strong. We've been measuring them with our lattice enthalpy. They're very big numbers. So how is it possible that we can break that apart simply with water? And it's all really to do with that temperature change that occurs when they dissolve. Some are going to be exothermic and some are going to be endothermic. And this is also with a balance between how much energy I need to put in to break the ionic lattice, so the lattice enthalpy, compared to how much energy I'm going to get back when water gets attracted to those ions. So water has positive and negative parts to it, delta plus and delta minus, and the ions are positive and negative, and so there's going to be some attractions, and when those things attract and attractions form, energy is released. Now if more energy is released than is needed to break the lattice, we're going to end up with an exothermic change. We're going to end up with a solution, a solid that can dissolve. If we need to put more energy in than we're going to get back from the water, then it might not dissolve without some heating. So let's have a look at what happens. The first thing that happens when we put an ionic solid in water is that the lattice, the ionic lattice, so remember our diagrams from earlier in the course, and the ionic lattice is the alternating positive and negative ions. They break apart, those ions break apart, and that is called the lattice enthalpy. So they become free to move, completely free of each other, no attractions, gaseous ions. So they break apart, and that is the lattice enthalpy of dissociation. You have to put energy in. So you're putting in an amount of energy. Positive, you've got to put energy in, so you're going up on your energy diagram, and then you take those ions. I'm just going to draw two for ease of space because we haven't got a lot of space, and water surrounds them, so the water molecules surround them. So if you think about the positive ion and then you draw your waters, well, which bit of water would be attracted? Well, oxygen is the negative part of water, so all of a sudden the waters start to surround and form attractions to the positive ion, and those attractions release energy. And if we do the negative ion, we'd need to put our waters the other way around, so the H's might attract. Yeah, so we've got water attracting via the hydrogens or the oxygens, depending on which ion you're attracting to. And that is going to be a negative release of energy. The difference between these two, so we've put some energy in at the beginning, that was our lattice dissociation. We've got the gaseous ions at the top, and then we've got some energy back from surrounding them by water. This is called hydration. The difference, this little difference here, that is our enthalpy of solution. And if the hydration is bigger, like the example that I've just drawn here, if the hydration is bigger, we're going to end up with a negative number. So if there's energy left over, we'll end up with a negative number. So this would be like this, and we would say this was exothermic because we had energy left over. So this is where we had a profile like this. So this was our lattice dissociation, and this was our hydration. If not enough energy is taken in, we're going to have to take it in from the surroundings to get it. So we're going to have to heat this up to get it to dissolve. That's when our lattice dissociation is bigger than our hydration. We end up with either a negative exothermic or a positive endothermic change. So see if you can summarise that. When will it be exothermic? When will this be endothermic? There we go. If it's exothermic, more energy is released, so the down part is bigger than is needed to break the lattice up. We end up with a negative overall amount, so more released than taken in. But if it ends up endothermic, more is needed to be taken in than is ever released. So we're going to need to add extra energy ourselves to get it to dissolve. So let's just have a look at the terms that we've been talking about, the definitions for these terms. So an enthalpy of solution is defined as the enthalpy change when 1 mole of an ionic substance dissolves to form an infinitely dilute solution. It dissolves and it's not going to be coming out of solution. So when there's enthalpy, when 1 mole of the ionic solid dissolves. So you may just see it written like this, NaCl solid, 1 mole of it makes Na plus Aq and Cl minus Aq because ions are free. You may well see somebody writing in plus Aq here like this in brackets. I'm going to put that in brackets there. You can do that, but don't write plus H2O, because if you write plus H2O you have to balance it, and where it's not reacting with the water, it's just dissolving in the water. So you don't need to write that plus Aq part, you can just show the solid dissolving, which is what I tend to do. And the second thing we've been talking about is the enthalpy of hydration, when 1 mole of gaseous ions become aqueous ions. So we're turning gaseous ions into aqueous ions. So if we did that for sodium, we take sodium gaseous ions and we become sodium aqueous ions. If we do that for chloride ions, chloride gaseous ions become chloride aqueous ions. Enthalpies of hydration are always exothermic. Energy is always released when they form these bonds to water. They're called ion dipole attractions. So in the final section of this video, we're going to work out how we can calculate this enthalpy of solution and do a little cycle. So it can be calculated from that lattice dissociation value and those hydrations. So we're just expanding on our simple profile that we drew earlier on. We started with our solid down at the bottom here, and the first thing we did was we broke it up. We did lattice dissociation. So we broke it up, but that's 771. What does lattice dissociation refer to? Well, it's NaCl solid becomes Na plus gas and Cl minus gas. So I'm going to put those two on this line, Na plus gas and Cl minus gas. I use the energy to break up the lattice. And then hydration refers to taking the gaseous ion and making it aqueous. And then we've got the same for this one, Cl minus gas becomes Cl minus, and we had those as our exothermic amounts. So we do one at a time. Remember, with these Born-Haber cycles, you do one thing at a time. So we're going to do sodium first and leave the chlorine alone. So the chloride ion is still a chloride ion, and that was minus 406. And then you can turn the chloride ion into an aqueous chloride ion. That was minus 363. Now at the end we never actually know whether this final arrow here is going to point up or down in this cycle until we look at the relative magnitude, the relative size of these two values. This enthalpy of solution arrow here, this our unknown, x, is the only arrow that's going around our cycle in an anti-clockwise direction. So x is going to actually be equal to the lattice dissociation value plus the hydration value. So each of the hydrations added together, so that's the hydration of sodium and the hydration of the chloride ions. So if we put those numbers in, x is going to be equal to 771 plus minus 406 plus minus 363. And if you type that in your calculator, you should get a value of plus 2 kilojoules per mole. And now you can see why they drew that arrow pointing up, because it's a positive amount. So actually salt doesn't dissolve in water, and you might have that always perfectly. You might have seen that when you tip salt into a cold pan of water, it doesn't immediately dissolve, but you don't have to heat your pan up much to get your salt to dissolve. Now there is a little equation for this, so you don't actually have to draw a cycle all the time. It says the enthalpy change of solution, that was our x, is equal to the lattice dissociation plus the sum of the hydrations. But you need to be careful. This is only, you must understand where these come from, because if you have two CLs in your formula, like MgCl2, you are going to need to double the value for Cl because the number is for 1 mole and you've got 2. You do need to, when adding both of these, realise that you're adding two negative numbers, so you need to be careful with your signs as well. Sometimes an exam board want to try and catch you out, and instead of giving you the dissociation value, they give you the formation value, which will be the negative value, and you'll need to make it into the positive value by changing the sign. So you could mathematically rearrange it like that, or you could just do it in your head, change the sign to be the dissociation value. Let's have a go at another one. This one is different because there are two CLs in calcium chloride. So maybe the first thing you could do is see if you could write 3 separate equations for what those values at the top represent. There we go. They represent when 1 mole of the ionic lattice is separated into gaseous ions, or when 1 mole of gaseous ions become 1 mole of aqueous ions, or when 1 mole of gaseous chloride ions become 1 mole of aqueous ions. Now, this cycle's kind of been worked out for you already, and it's already showing an exothermic change. So we're now not putting our solid right at the bottom, we're putting it here, CaCl2 solid. We're going to break up the lattice and turn it into gaseous ions. That's our first step. We've got 2Cl minus gas, and that is the lattice dissociation, so plus 2258. And then we're going to hydrate it a little bit at a time. So we're going to hydrate the calcium, and there is 1 mole of calcium, so we don't need to double any numbers yet. So we're leaving the chloride ions as they are, so that is just the number -1577. But the next one, we are hydrating 2 chloride ions. So we've got 2 lots of -363. And then our unknown x is here. So we know that the enthalpy of solution x is equal to the lattice dissociation plus the sum of the hydration. So plus -1577 plus 2 lots of -363. So we mustn't lose our minus signs. And use your calculator, pause the video, work out a value for x. I got -45 kilojoules per mole. So that's why the arrow points down. So that's a relatively straightforward calculation, but you will need to practice it. You'll find some practicing of this in your problem solving booklet or in your study pack.